Today's lesson is about a different transformation called reflecting. So your reflection transformation is one that reflects the shape across a line of reflection. So remember when you're a small child and you'd paint half a page and then you'd fold the paper together so the paint would move to the other half of the page and be in a mirror image and would create a butterfly? That's what a reflection is. A reflection preserves the lengths of all the sides. They don't change after it's reflected. The angle measures are the same after the reflection, and therefore it's the same shape just at a different location, making it an isometry. And the key thing to know is that for any reflection, the pre-image, the original, and the resulting image are always equidistant from the line of reflection. And that's actually going to help you a lot when you're graphing out reflections, that equidistant rule. So here's your steps for graphing a reflection. First, graph the original shape and the line of reflection. Second, reflect each vertex, each corner of your shape, by measuring the perpendicular shortest distance of each point from the line of reflection. Connect the new vertices to draw your image. So we'll go through question 1 together using these steps. First, graph the original point, 4, 1, and graph the line of reflection. Now, quick note, when you see something written like this, the capital R stands for reflection. The subscript will tell you what the line of reflection is. So this is telling us that the line of reflection is at x equals 2. X equals lines are vertical lines. So we have a vertical line going through 2 on the x-axis. That's our line of reflection for this problem. And then it closes with what we are reflecting. In this case, it's a point 4, 1. So that's our pre-image, 4, 1. So step 2 is to measure the shortest distance from our pre-image to the line of reflection. Oh, it takes 2 units to get to the line of reflection. Notice how the shortest distance is perpendicular to the line of reflection. So the result, the image, will be the exact same distance from the line of reflection, just on the other side. Your end result of the reflection is at 0, 1. Pause here and try question 2 on your own. Check your answer for part A. This time it was a y equals 4 line of reflection. If it has just a y, no x, it's a horizontal line at 4 on the y-axis. The original point at -3, 2 was 2 units away from the line of reflection, so the image would be 2 units past the line of reflection. That ends up at -3, 6. B is tricky because when you do the reflection, it doesn't stay on the graph. Let's see if you're able to figure out the answer anyway. So when you graph your pre-image 2, 6, and you graph the line of reflection, you notice how your pre-image is 9 units away from the line of reflection. Going 9 units past, that goes off the graph, but you could still figure out where it would end up because 9 units here, 9 units here, that'd be 18 units down total. So if you go 18 units down from the original height of 6 on the y-axis, 6 minus 18, you'd end up at -12 units below the origin. So it didn't slide left or right, so it's still at an x value of 2. Your final answer is at 2, -12. The same process you use to reflect points can be used for each point in a more complicated shape to reflect your entire shape. So for example, for number 3, they give you a triangle to reflect. Go ahead and graph that triangle XYZ. Your line of reflection is on the x-axis. So take the corners of your triangle, and to reflect each corner, measure how far those vertices are from your line of reflection. Then reflect each point. So for example, if this vertex is 3 units below the line of reflection, its reflection would be 3 units above. Connect the new vertices, and you have your reflected triangle. Now, there's a shortcut that you can use only for reflecting over the x-axis. Here it is. I want you to notice that reflecting over the x-axis really just keeps the point values the same, except all the y values have the opposite sign. For example, for your original shape, you know how this point was at 2, 6? The reflection ended up at 2, -6. There's a version of that shortcut for reflections over the y-axis. It's just that for reflections over the y-axis, it would change all the x values to the opposite sign instead of the y values. Go ahead and try parts A and B for question 4. C is a bit of a challenge question. We'll go over that together. Pause here until you're done. Check your answer for part A. Check your answer for part B. Now, C is a special case. Think about that equation, y = x. That has both an x and a y, so it's not going to be horizontal or vertical. It's going to be more of a slanted line. You could say there's invisible 1 in front of the x and invisible y-intercept of +0. So the m is 1, the b is 0. So if you start at 0, and then you have a slope of 1/1, it's going at a slant like so. So that's your line of reflection. When you have y = x as your line of reflection, you really want to make sure you're counting the distance of each point to the line of reflection using the grid marks that are already there. So in this case, you're not going to do perpendicular distance. For example, for this one here, you don't want to count perpendicular distance because that can get complicated and you'll end up with a lot of half units, which is a pain. Instead, you want to count on the grid marks that are already there until you get to the line of reflection. So here it would be 8 units. And you could go either horizontally or vertically. You just have to work with the grid marks that are already there in one direction or another. So I could have drawn this here or here. It would have been 2 units either way. And then here's where it gets weird. Instead of going straight across and continuing this line in the same direction it is, 8 units, you're actually going to make a right angle and go up at 8 units. And for this one, you make a right angle, go down 2 units. For this one, you make a right angle, go left 2 units. And that is your reflection. Pause here and try the last problem, parts A, B, and C, on your own. Check your answer for part A. Check your answer for part B. Notice how if you're reflecting a point that's already on the line of reflection, that's a 0 unit reflection, so the reflection is on the same place. And check part C, the trickiest one. Now that you know how to graph the y = x reflections, graphically, here's a more algebraic way to figure out the new vertices. Anytime you reflect a point across the line y = x, you get a result, you get an image that is the same point, but backwards. So I want you to see how your original point S, 6, 1 here, reflected to become 1, 6 here. It's the same point, just the x and y values got swapped. And that's true for all the vertices. Great job today, guys. Don't forget to turn in a picture of your notes on Schoology when you're done.